Okay, thank you very much for accepting to give a talk here. It's a pleasure to be in this conference. My colleague Niels talked about science. I'm afraid I'm going to talk about econometrics today, as you will see slowly in my talk. My problem is how to balance my budget. I don't want deficits and I don't want surpluses. So, and at the same time, I don't want to upset the people. Grid points are my people and mass is my money. So how can we do that? Well, before we do that, a few things about my talk. First, I'm going to speak about the mass conservation properties of IFS. I'm going to say a few things about the implementation of this, of a few mass fixing schemes which I have selected. Results from testing these schemes on humidity and cloud fields. And then I'm going to present a few results on testing these schemes on tracers. So, why we want to do this mass fixing business? First of all, semi-Lagrangian advection is not formally conserving. And the reason it's not formally conserving is because there are certain inaccuracies in the scheme. There are inaccuracies in calculating the trajectory. The trajectory calculation is purely geometrical. Is not constrained at all by the continuity equation. There are certain simplified assumptions and numerical errors that are done during this calculation. In addition, there is interpolation errors, which are connected with the interpolation of the field to the departure point. At a practical level, non-conservation is not a big issue for global NWP forecasts. And for this reason, there are a lot of semi-Lagrangian models that are quite successful, and they are not formally conserving, and hasn't bothered so far too much. It's not the same, of course, for climate. And conservation is becoming more important now that we are running models with a lot of chemical traces, aerosols, volcanic plumes, etc. So, a few things about the IFS model. Niels has already given a very good explanation of this, so I will only say that it's a spectral semi-Lagrangian spherical harmonic scheme, semi-implicit time stepping, two-time level, and is using a finite element discretization in the vertical. It does have a linear, it has a Gaussian grid, linear Gaussian grid, and it is unstaggered, it's an A grid. This grid we compute the trajectories, the semi-Lagrangian trajectories and physics. The continuity equation that is used in IFS is based on the Ricci and Tanguy formulation, 1996, and it's good for us because it alleviates the problem of spurious orographic resonance. In fact, a slight modification to this scheme is used where the orography field is extracted from the advected field, which is the logarithm of the pressure, surface pressure, and that gives better accuracy and improved conservation. For example, if we take a 10-day forecast, the IFS model gains about less than 0.02% of the initial mass. So it sounds good, but if we consider rougher fields, such as tracers, like cloud fields, conservation is not that good. Not that bad to bother us a lot so far, but as we are adding more and more tracers, such as volcanic plumes and other things, you see that you may have problems, chemical traces. So how can we fix this problem? One simpler approach is mass fixers. What do? They are applied a posteriori after you have advected your field, and they restore conservation. They are low-cost algorithms and they are easy to implement. They can guarantee global mass conservation, but they are not local. So that's why you have seen so far a lot of talks on inherently conserving scheme, and some for semi-Lagrangian, semi-implicit methods. Some of these examples are CSLAM, LMCSL, SLICE, etc. This is a more sophisticated approach, but it requires complete restructuring of your economy. So you have to work harder to achieve this, and implementation is a complex task, and it's computationally more expensive approach. So let's see what can we do if we stay with mass fixers. Now, one very simple mass fixer that existed until recently, it still exists in the IFS model, is the so-called proportional fixer, which comes from a paper by Williamson and Rush. It's a simplified version of that. What it does is just to scale every grid point value by the same percentage. So it takes the same percentage of mass, or gives the same percentage of mass to each grid point, according to, depending on if you have surplus or deficit. So it's a simple taxman approach. Takes the same from everybody. That's not very good if the solution is accurate, because it will reduce the accuracy of the solution. So there are people that have published papers on more sophisticated approaches, mass fixers, which they have some local features. What they do is they correct proportionally to some error measure. So they introduce a small correction in areas that the solution is smooth, and larger corrections where the solution is not smooth. And additionally, they can achieve quasi-monotonicity. They don't generate new extrema, new maxima, and new minima. And some examples is these schemes: Priestley algorithm, Bermejo-Conde, and more recently the Zero-Cut scheme. And now let's see a few things about this Bermejo-Conde algorithm. It was published in 2003, and what it's trying to achieve is that we have this quasi-monotone solution phi. It tries to find a new solution which minimizes the distance from the original solution, subject to the constraint of mass conservation. It corrects locally in proportion to the interpolation error message, and we can see that there. So we have this weight here introduced, and this weight depends on some error measure, and this p is a node number, and this is a sign of your imbalance. So if you have, for example, you have surplus, this is positive. If you have less mass in your system, this is negative. If you have deficit. And this lambda is the Lagrange multiplier. So this scheme, when we have more mass than we want, we'll take away mass from grid points, and that will be proportional to this quantity here. If it undershoots, we'll take mass, but otherwise it will set 0 to preserve monotonicity. And in the original, just a few things to say, that in the original algorithm, the author suggested to use p equals 3. I found that that was a little bit too harsh in an operational model. For example, if you run for a few time steps, you tend to have accumulations of, this is the cloud ice water content, around 650 hectopascal height. And we see here, this is a run after 2 hours without any fixer. This is with this Bermejo-Conde fixer. And what it does for P equals C, it generates some very small numbers, big numbers, that these amount to large increments, that they grow rapidly, and then the model destabilizes. So I found that it's not really important to use such a high coefficient. P equals 1 is sufficient for our purposes and maintains quasi-monotonicity. So if we go to a similar scheme, it's a Zero-Cut scheme, which also distributes total mass imbalance locally, proportionally to an error measure. Very briefly, we can write this scheme this way. And we can see the locality again, because this gamma depends on a local error measure. I should say that this scheme, as described in the paper, mentions about different ways of approximating this high order and low order, this difference. You can use a cubic, for example, Lagrange interpolation formula for your H, your high order solution, and a linear for your low order solution. Now we can show that although this is not designed from a minimization principle, it is very easy to show that it minimizes again this norm. And in fact, this is the Lagrange multiplier for this scheme. So these two methods, they are close if we consider the same way of estimating the high and the low order solution. One nice thing with this scheme is that it tends to produce smaller increments than the previous one, and I will show you some results later. And On the other hand, sometimes if you're really worried about monotonicity, it may break monotonicity sometimes after a few points. So these are some results with the Bermejo-Conte scheme applied to the cloud liquid water content at approximately 850 hectopascal height. On the left is the actual field at 12 hours forecast, and we can see that it's concentrated over the ocean. These are frontal areas. And on the right, we have the correction that the algorithm computes at that particular time step. Probably you cannot see very well the scale here, but this is almost 2 orders of magnitude smaller than this. And first, we see that the correction doesn't generate corrections in areas that are dry, which is good. The other thing we notice is that although it is on areas that there is moisture, is not exactly is not the same shape as this. For example, the proportional fixer would have generated the same picture, but with smaller magnitude. Here there is some variation, and that variation depends on the errors, the differences between the cubic and the linear interpolation. So we can see the local nature of the scheme. Now, if we compare with the zero-cut scheme using the linear and cubic interpolation, on the left is the correction computed by the Bermejo-Conte scheme, and on the right is the correction computed by the zero-cut scheme. These are similar, but we can notice here that the zero-cut scheme produces increments that are more spread out, slightly smaller in magnitude. What I noticed in that particular run that occasionally breaks the minima and the maxima, it will generate new ones. For example, in this case, I think it did something about 0.25% of the total number of grid points at few time steps. Now, if we move to the next algorithm, the Priestley algorithm, this is also this is a popular algorithm, has been used for several years in models such as the HAT-GEM, I believe, which is the climate model of the Met Office. What it does is trying to find the maximum possible coefficients alpha j, and blends two solutions, the high order solution H and the low order solution L. And it's trying to find the maximum possible weights so that you stay closer to the high order solution, subject to the constraint of mass conservation and quasi-monotonicity. This is the surrounding points, the points surrounding a field phi at the grid point j. It is also a local scheme, but it is also an iterative scheme, which means you start from a solution with the cubic Lagrange, for example, and in order to satisfy these two constraints of monotonicity and conservation, it has to iterate. It takes more than one iteration, and my experience with that is that it usually takes 3 iterations for the cloud fields. It might take more for some other fields that are rougher. However, it converges very quickly if you provide a high order solution which is already filtered. And here, what do I do when I say Priestley against Priestley is, I mean the standard scheme as described in the paper, where we start from the cubic Lagrange field and you correct it, and this is the correction for the same field, cloud liquid water content at 850 hectopascal height approximately. And this is the same algorithm, but now I'm not starting from the cubic Lagrange. I'm starting from a filtered cubic Lagrange. I have applied a quasi-monotone filter. And it's interesting here to see that this has positive and negatives because it has to work harder. You have overshoots, undershoots. In order to fix quasi-monotonicity, it will work both ways. It will create more variability. It's a better modern art picture, perhaps. Where this one, it's more similar to the schemes I presented before. And now, the question is how much different are these schemes? So if I take this Priestley algorithm, for example, and I compare it with Bermejo-Conte, and I take the increment they produce and I accumulate it over 24 hours, and then I scale it per time step, and I take the difference from these two algorithms, I get this. What is this? This is about a small quantity. It's about 2 orders of magnitude smaller than the increment itself, 2 to 3 orders of magnitude, which perhaps tells me that although the two algorithms are different, quite different, they kind of converge to the same solution, which hopefully is the right one, if the word converge is permitted in that context. So let's see some time step statistics with respect to these schemes. So what I've done here is I have taken some statistics from the model. I am picking up the maximum correction per time step for each of these algorithms, and I'm scaling it with the RMS norm of the correction of the field that I'm correcting, and I multiply by 100 to get the percentage. So we can see here that the Priestley scheme, the classic Priestley scheme, it produces larger increments. The line below is the Priestley field with a quasi-monotone filter. Then the two ones at the bottom is the Bermejo-Conte scheme and the zero-cut scheme, which produces smaller maximum increments. If we move to the right plot, it's something similar, but now I'm looking at the norm of the correction with respect to the norm of the field. And again, I see similar picture. So here I have the Priestley scheme, which produces the biggest correction, biggest magnitude. Then it seems that the Bermejo-Conte and the Priestley quasi-monotone scheme are more or less the same, and the zero-cut scheme produces the smallest correction. Now, so what happens if you put these schemes into the real test? So if you run, well, not so real because I haven't used data simulation. It's a simple verification experiment. So I'm doing a 10-day forecast. I have 14 cases. They differ by 4 weeks. You start 1st of January 2011, you go on. And what I found is that the impact of these fixers is generally neutral. It's absolutely neutral with respect to the anomaly correlation coefficient. This coefficient is, it tells me how much the model, the forecast is correlated with observations. And a perfect forecast will give me 100% anomaly correlation. A bad forecast, but any forecast to be useful should be 60% or above, because otherwise the climate beats it. So no problem in terms of anomaly correlation coefficient. One slight problem with the RMSC at upper levels in the tropics. But I have to say that at that region the IFS model is sensitive, and you can do sometimes, well, what small changes can create a bigger RMSC error there. The worst of these fixes was the proportional. The Bermejo-Conte, the Priestley, and the zero-cut are at this line in between. And here I have applied one of these fixes only on humidity, so you can see it's half the way up. But then you can do other things. For example, increasing the cubic interpolation, increasing the order of interpolation in the cloud fields, and then you get an increase in the RMS where maybe you would have expected to get a better solution. Now, a few results about volcanic plumes. So this is the Grimsvotn volcanic eruption, which happened last year, in 21st of May, I think, yeah. And this is the plume spread after 6 days, provided by the Met Office website. And this is a simulation with the IFS. This is a 6-day forecast of the volcanic plume. And this is with a scheme without the fixer, and this with a fixer. What is important here to see is that because the fixer diagnoses a large surplus at initial steps, it tries to cut the mass to restore the conservation. And because everything is concentrated in a small area, you end up with a more damped solution, a solution with lower minima, which maybe is not such a good thing for experts in that field. That's what experts in that field say. There are also differences between quasi-monotone and non-quasi-monotone solution. If you choose a smoother field, like C or carbon monoxide, you don't see this problem, and there are small differences between the fixer, the solution which is fixed, and the other solution. Now, to finish with my talk, so what we can say about this fixer is that corrections computed by Priestley, Bermejo, Conte, Zerocat schemes on moisture and relatively smooth fields are small in magnitude, which is a good thing, and similar. The Priestley requires iterations and it can be more expensive. Sometimes may not converge. I haven't found this in my case studies, but I understand it can happen. The Bermejo and Conte Zerocat schemes are better options because they are cheaper. The Zerocat scheme seems to be the one that produces smallest, more diffused increments, but occasionally may generate a new maxima and minima. And applying the fixes on very rough fields can be reduce the extremes, which may not be good in some cases. But overall, this is a difficult problem for a global semi-Lagrangian model, which you have to advect a step function at a relatively coarse resolution. Okay, thank you for your attention.
Any questions? Please, Roda.
So while fixing the mass locally, do you also consider the mass variation due to precipitation and evaporation in the continuity equation?
Yes, I have applied that on all these fields. Humidity, cloud, liquid contact, ice, advected rain, and snow.
So this error is different from that? What?
To be honest, we haven't looked all of the plots, but it has this pattern. I cannot remember now about rain and snow because I haven't looked very much this. I have looked more the cloud, liquid, water content, and ice, and humidity. Humidity is smoother, and in fact, in terms of conservation, humidity is the model is quite good in humidity. It's maybe 100th of % or less, the global imbalance. It's the cloud, liquid, water, and ice, which are rougher, that are less conservative in IFS. And I suspect it most models.
How do you handle variation in the vertical? Do you do it layer by layer or what?
Well, the algorithm takes global sums over 3 dimensions.
So, oh, okay, changes
So,
all levels altogether.
Yeah. First, you do in the horizontal, you use the areas of the boxes, and then in the vertical, integrate the vertical. Sorry, I think it's the other way around. First, I have to find the total column, and then integrate.
Water mixing ratio is very tiny a lot, but you bundle them all together.
Yes.
Are there any other questions?
Just one comment. You can improve further result if you use a less diffusive monotonic filter.
Sure. Yeah.
And then you lose less mass, and then these fixers do less work. So you get even a bonus, because a lot of this loss of mass, especially when the field is not smooth, get lost by the monotonicity filter. You clip a lot of.
Yes.
Yeah.
Yes, very important. Yeah, I agree. I haven't looked at this yet. Yeah.
Yes.
Anybody else? Well, in that case, let's thank our speaker again.